Hey, hello, welcome guys. Yeah, I want to build a ring theory lecture. So basically, it's basically from the abstract algebra view, you should start from the group theory and go into ring theory. Yeah, so if you haven't seen my group theory lecture, yeah, I think it's fine. Yeah, I mean, you can check. Okay, but basically, I just recommend some textbook, which is the I think the elementary one is first 10, and also this book is very good. I mean, you can buy one and spend a lot, maybe whole your life to study this book. Yeah, so there's there's a lot of things to. You can view this book as a dictionary, and I up to now I still learn a lot from this book. Yeah, and if you will try to learn in algebraic geometry, you can follow Harshon or this Vekal, the rising sea of algebraic geometry, which is interesting. Yeah, so by the way, I built up this mathematical video for rings, not just I mean I'm not show off or something. I just feel like I like mathematics and I will try to make a record. Or you can basically I just pretend I'm very good. Okay, so okay, yeah, but if you have any idea, then you just post a comment below. Okay, so this video basically is just from introduction, and we will start from because commutative algebra is very difficult, so we start from one by one, and yeah, hopefully we feel some detail. Okay, so definition. So let's start from a non-empty set. So let's say we have a non-empty set R is said to be associative ring. So basically, it's called ring if it has two operations. One is a plus, one is product. So plus is not just plus. The plus is not usual addition, and this is not usual times, just two operations. Okay, so such that R plus forms a abelian group. Yeah, so basically you can view that you can write down as A plus B, B plus A, and A plus B plus C equals A plus B plus C. Also, there's a zero you can add. And then there's a minus one, minus A, which is zero. So it's inverse, and I use addition. Okay, and that's talking about the multiplication. So you get A, B. So your A times B must be in R. So it's closure. There's no there's no necessary inverse. Okay, but the associative is must be satisfied. So these two should be also a semi group. So semi group in times. Okay, so sorry, yeah, use this dot. Okay, so basically it's the same as this times. Okay, and also you should be able to do this. So this is just the distribution law, right? So B plus. Okay, so for every ABC in the ring. So from everything works for all of these called a ring. So ring. Okay, and if AB okay, so if AB the same as BA, it's called a commutative ring. Basically, commutative ring is so by the way, I just want to say the commutative ring is very important in algebraic geometry. So if you're talking about the variety, let's say if you just take some polynomial ring and let's say for example let's say xy, right? So this will function ring. So basically there's a lot of commutative ring, not just obviously one, right? You can take the quotient. So for example you can also check this, right? This is a commutative ring. Okay, so the commutative rings is very rich. Okay. Okay, but this is some hardcore example. The simple example is that you just get an integer. Right, so integer is a ring. Check by yourself. And also you can take the even integer. Okay, it's also a ring. Also you can check that if you take a ring to be 3, the integer which is multiple 3, or basically actually is going to multiple of A, which A is another integer. Is also a ring. Okay. Also, a rational number is a ring, and also complex number, real numbers are also a ring. Okay. And these are ring basically special called field. Yeah. So we will talk about a field theory. It's not field theory in the physics, in the field theory in the abstract math. So basically, the field is defined to be a commutative ring if there's a inverse, right? Yeah. So the usual starting point is that from group, go to ring, go to field, and the field you can talk about Galois, and then you can talk about the module, and talk about more, right? So it become an exact sequence homological algebra. So this should be and then you go into category. Yeah, so this is basically what I plan to do in the future. Maybe I need to do 4 year, right? But I want to build this path. Yeah, so somehow I already made some in the group theory and the ring and the field. Yeah, so this is what the line I want to produce. Maybe I will spend 1 year. Okay, so hopefully not 10 years. Okay, and also R can be viewed as there's an example is mass 7, right? So you can check that in the mass 7 you can talk about the inverse. You can talk about the multiplication mass 7, addition mass 7. Okay, however, okay. Yeah, these are all commutative ring, and then you can talk about non-commutative ring. But I don't want to. Right? So one obviously non-commutative ring is called quaternion. You can write A0, A1I, A2I, A2J, A3K, and these are all complex, all the real numbers. And then you satisfy the I squared, J squared, K squared is -1, and IJ is negative JI, IK is negative KI, and KJ is negative JK. Yeah, this is called a quaternion. Quaternion. Yeah, which is a non-commutative ring. Okay, and the interesting is that any non-zero element still has the inverse. Yeah, so this is called a division ring. But don't worry, I will talk about examples. I will talk about the definition. I mean, I just don't want to spend time on. I just don't want to spend time on examples. I guess you guys can find example. Okay, but now we want to talk about special case of ring. So there are a lot of rings, notarial ring or something, right? But since this is elementary, so we talk about some idea. So let's say if R, so we work in a commutative ring. Okay, so if A is non-zero, A is 0 in R, say to be zero divisor, So zero divisor means that you can find a B which is non-zero, such that AB is 0, right? So this thing do not happen in the real numbers, right? Because in the real numbers, if you're non-zero, any non-zero times two non-zero product must be non-zero. Okay, so this is somehow the generalization of the usual ring. Okay, then the next is a famous called integral domain. So integral domain means that if AB is 0, implies A is 0, B is 0, or B is 0. Yeah, this is called integral domain. Okay, so basically every, for example, your usual real numbers is integral domain, complex number, rational number, are integral domain. Basically, any field is an integral domain. Okay, let's say a non-integral example. Let's say, for example, let's see. Let's say if in F4, right? In the F4, basically it's everything mod 4. Then 2 times 2 is 0, right? Because 2 times 2 is 4, which is a 0. In the mod 4, but the 2 is not 0. Okay. Yeah. Also, you can build some quotient, for example, RxY module. So real number XY module X times Y, right? So X times Y is 0 by definition, since it's quotient, but the X is non-zero and Y is non-zero. Okay, so another definition. So this is the field. So field is defined to be commutative division ring. Division ring. Okay, so what is division ring? So division means that non-zero element has inverse. So if every non-zero element has its inverse, it called division ring. If it's commutative division ring, then it called field. Okay. So for example, rational field, real number, complex number, finite field, both field. Division ring is basically quaternion. Yeah. A division ring is not easy to see, right? But somehow like maybe hard to construct. Okay, so there's many stupid formula, so I just list. So these are basically leaf exercise. What the hell is going on? Okay. So like A0 is 0, A is 0. So this is for all ring, and then your A minus B is minus A, B is minus AB. So these are all just stupid exercise. So you guys should check by yourself. But at least one is multiplication one. Okay. So if one is this, you can talk about minus one. Okay. So also this. Okay. Also you can check for the commutative. If your ring is commutative, then you can check your lovely high square results: x squared plus y squared plus 2xy. Yeah, so basically, if you talk about high school, if you talk about general commutative ring, then you will have the, let's see. Yeah, basically, I want to say that in a general commutative ring, since it's commutative, right? So xy equals yx. So you can talk about xy squared equals to this. And then you can check that your binomial coefficient is also this is also work. So this is work in a general ring. It's not just the real numbers or the integer or something. Yeah, so I just want to say this also work. Yeah, it seems like we still have a lot to say. Yeah, but yeah, before we finish, maybe let's prove a thing. Okay, so let's prove a theorem. So remember that we talk about the integral domain, right? So let's prove a finite, let's say a finite field, a finite integral domain. So given a finite integral domain will be a field. So any finite integral domain will be a field. Okay, so this is what I intended to prove. Okay, so let's see a proof. Yeah, so we know that the integral domain is a b equals to 0, where implies a equals 0, b equals 0. And we need to use a finite property. So basically, we need to prove that any. Oh, by the way, when we define integral domain, we already assume that it must be commutative. Okay, so basically, we need to prove that there's an inverse. Okay. So basically, we need to show that the inverse exists. So if the inverse exists, then everything will be trivial, right? Because the integral domain is already commutative. And also, we just need to prove the inverse is. If inverse exists, then when we definitely have the unit. Okay, so yeah, let's see a proof. Okay, nice. Yeah, so let's see. Let's suppose this D is by finite integral domain. Okay, so let's see. We need to prove there's a 1, right? And the inverse is. So let's see. Let's say we have all the elements D. So let's say D is just this. And then we take A is non-zero in D. Right, so we pick A is non-zero belongs to D. Okay, this is what I intended to do. Okay, so Let's consider this following set, which is x1a, x2a, up to xna. Okay, and and we know that it's a closure, right? So they are all in D. But the problem is that they cannot be different, right? They cannot be the same. So if they are the same, if you get two are the same, you get xi xj, a equals xja, so you get xi minus xj, which is 0, where you get xi equals xj or a is 0, right? But you know a is non-zero and xi cannot be xa by definition, right? So which they are all different. So they all must be D, right? They must be D. Okay, so that means any y belongs to D can be written as y equals to xia for some I. Okay. Okay, but now you know that the A belongs to D, right? So A must be written as xia for some xi. So A must be xia for some xi, right? So let's say this is called I0, right? So there's always I0, right? But I know that this is commutative, so this is AXI0. Okay, so then you see that xi0 is a unit. Okay, so you know there is a unit. Okay, and if any y belongs to D, we know that the y is xia for some xi. Right, for some xi, y is xi times a. Right, we know this, and then we know, so we get y xi0 is basically xia times xi0, and then they are commutative, so xi axi0, right? This is a, so it's xia y. Okay, so from here that you know what you know, your xi0s will exactly be the same. So this proves that xi0 is exactly the unit, because now if for every y, right, for any y, it must be the same, right? So not just for a. Okay, so now let's let xi0 to be 1. Okay, so I just call it 1. Okay, but by definition, right, for 1 always be xa, right, for some xia, right? So this xi will be the inverse. Okay, so for each a, there is always xi. Okay, so by definition, we get the inverse and we get the unit. So we prove the results. Okay, in the next video, let's talk about more other results. I think it's enough. See you guys next videos.